Hi, my name is Brian Caffo, and this is Mathematical Biostatistics Bootcamp, Lecture 5 on Conditional Probability. So in this lecture, we're going to talk about conditional probabilities and then the associated density functions for calculating conditional probabilities, basically just called conditional densities, and we'll talk about conditional mass functions for discrete random variables. We'll talk about Bayes' rule and then briefly talk about an example of Bayes' rule using diagnostic tests, and then we'll talk a little bit about so-called diagnostic likelihood ratios. So let me give you some brief motivation for conditional probabilities. I think we kind of internally do these things pretty easily. So imagine rolling a standard die, and we're assuming that the probability of each face is 1/6. Suppose you didn't know the outcome of the die, but someone were to give you the information that the die roll was odd. So it had to be a 1, a 3, or a 5. A 2 or a 4 or a 6 is not possible given this extra information. Then conditional on this new information, everyone would probably agree that the probability is now 1/3. And all we're going to do in the next couple of slides is mathematically develop these ideas a little bit more completely. So let's develop the notion of conditional probability just generically talking about events. So let's let B be any event such that the probability of B is greater than 0. This condition is kind of important because it doesn't make any sense to condition on the probability of an event occurring when that event cannot occur. So it doesn't make any sense to talk about the probability of A given B occurred if the probability that B occurred is exactly 0. Just to put this in words, it makes no sense to talk about the probability that a coin is head given that the coin is on its side if you're not going to allow for the possibility for the coin to land on its side. So the definition of a conditional probability of an event is the probability of the event A occurring given that the event B has occurred is the probability of the intersection divided by the probability of B. Now, notice if A and B are independent, then the probability of A given B, well, the numerator component, the intersection, A intersect B, factors into the product of the two probabilities, probability of A times the probability of B. The probability of B cancels out in the numerator and denominator, and you're left with the probability of A. So this actually makes a lot of sense that if the events A and B are independent, then the probability of A, given that B has occurred, is simply the probability of A without knowledge of whether or not B has occurred. That is, the information about whether B has occurred is irrelevant to the calculation of the probability of A. This matches our intuition as to what independence means, and it's nice that the mathematics works out that way. In fact, in some probability texts, this is their definition of independence as opposed to the definition that we gave earlier. So let's just work through the formula given our example with the die roll just to convince ourselves that it's actually working. We want the probability of a 1 given that the die roll is odd. So in this case, B is a 1, 3, or a 5. A is just a 1. So the probability of A given that B has occurred is the probability of the intersection. And in this case, A is the set containing 1, B is the set containing 1, 3, and 5. So A is a subset of B, so when you intersect the two, you just get A by itself. So it works out to be the probability of A divided by the probability of B. The probability of A by itself is 1/6. The probability of B is 3/6, and we get 1/3, exactly the answer that our intuition told us. Okay, so that ends our very brief discussion of basic conditional probability calculations using the standard events and generic discussion of probability. Next, we're going to talk about conditional densities, which will be our mathematical formulation for conditional probabilities for continuous random variables. So welcome back, troops. We're going to be talking now about conditional densities now that we know a little bit more about conditional probabilities. So conditional densities or mass functions are exactly densities and mass functions that govern the behavior of a random variable conditioned on the value the other random variable or another random variable took a different value. So just to tie this down a little bit, let's let f of x comma y be a bivariate density or mass function, and it governs the probabilistic behavior of the random variables capital X and capital Y. Now, I'm going to abuse notation slightly and let the letter f be the joint density and f of x be the marginal density associated with x, and f of y be the marginal density or mass function associated with y. And it's probably not the best notation to use f for the joint density, f for the two marginals when they are all referring to different things. So, just keep in mind that the arguments are kind of differentiating what I'm talking about here. This is exactly very sloppy notation, but I'm using it anyway. So just to remind you, the marginal density f of y is the joint density f of x comma y integrated over x, or if the random variables happen to be discrete, then f of y is the joint mass function f of x comma y summed over x. So in other words, if you want to know, regardless of what happened with respect to x, what is the probability behavior of the random variable y, you have to integrate over the random variable x over all the potential values it could take with what probabilities, and then you get the marginal behavior of the random variable y. In similar, you could get the marginal for x. F of x is the integral of the joint density over y, or the sum of the joint mass function over y. Well, the conditional density is exactly, say, for example, f of x given y is the joint density f of x comma y, or mass function, divided by the marginal f of y. It follows actually directly from the definition of conditional probabilities that we just gave you a couple slides ago, and that we sort of all agreed on made a lot of sense. Let me elaborate on that point. It's, in fact, in the discrete case where x can only take so many values, 1, 2, 3, 4, then this definition of conditional probability is exactly the definition that we used from events, where A is the event that x equals x and B is the event that y equals y. So there's no confusion. It exactly agrees with our definition of conditional probability. The continuous one is a little bit harder to kind of motivate why this is the definition. The event that x takes on a specific value or y takes on a specific value has probability 0 for continuous random variables. And so that kind of fails our basic premise from conditional probability associated with events, that the probability of the event that we're conditioning on has to have probability greater than 0. Now note, we're talking not about conditional probabilities, we're talking about the construction of conditional densities, which govern the behavior of conditional probabilities. So we haven't violated that rule from earlier, but it still kind of seems to break the spirit of the rule. And how do we get at this idea? How can we have a meaningful definition of the probabilistic behavior of a random variable given that another random variable takes on a specific value? Well, here's the motivation that I like. So imagine if you define the event A that the random variable x is less than or equal to a specific value, little x, and the event B is that the random variable y lies in this interval from y to y plus some small amount, say epsilon. Then now A and B are events that have positive probability, and we can apply our standard definition of conditional probability to talk about the probability of the event A given that the event B has occurred, right? That would just follow from our standard definition. So actually, let's formulate this. So the probability of A given B is the probability of x being less than or equal to little x, given that y is in the set y to y plus epsilon. And then now in this case, nothing has probability 0. We can just directly apply the probabilistic formula. And I don't think this is terribly important for this class. I just wanted this argument to be here for those who want to see it. But then you could just follow through the arithmetic, or not the calculus here, and get that basically this construction yields the conditional distribution function associated with the x, given that y equals y, as we let epsilon get smaller and smaller. So as the conditioning event gets closer and closer to y conditioning on it being the specific value y, we limit to a conditional distribution function associated with x. And then remember that density functions are derivatives of distribution functions. So if we just take the derivative of this, then we get the conditional density function. So we can see right here that if we differentiate this conditional distribution function, we get exactly the definition of the conditional density that we gave you before, f of x comma y divided by f of y. So if you're interested in this at this level, then you can go through those arguments carefully. And to be fair, these only cover the definition in the continuous case when we have differentiable distribution functions, but this is more than enough for our case. If you're interested in it at a deeper level even than this, where you have mixed continuous and discrete densities, then you can take an advanced probability course somewhere. But for our purposes, this is enough. And so just to summarize, we have the conditional probability definition associated with events that kind of governs all of our thinking about conditional probabilities, and that's the probability of A given B is the probability of A intersect B divided by the probability of B. And then in the event that you're talking about random variables, where we want to talk about the probability of a random variable x, given that the random variable y is taken on a specific value, it's the joint density or mass function divided by the marginal. And it has a nice sort of parallel with the probability associated with events. And here we've gone through the arguments to show how we get from these statements about events to this definition for mass functions and density functions. So conditional densities actually have a very nice geometric interpretation. So if you have a joint density, f of x comma y, that's a surface. F yields the z value, and xy is the plane. So f of x comma y is a joint density, is a surface, and its volume under the surface has to be 1 for it to be a joint density. Well, what does it mean to get the conditional density of x given that y takes a particular value? The event that y takes a particular value, that's sort of like a plane. At the point, let's say y is 5, at the point y equals 5, that's a plane. And that plane slices through this surface and yields a function. That function is just f of x comma y evaluated at the point 5, f of x comma 5. Okay, so we have this surface, we have this plane, the y equal 5 plane that cuts through the surface. And then we have the function that is on that plane at f of x comma 5. And that is exactly the conditional density, with the exception of now it doesn't integrate to 1. So we have to normalize it by something that integrates to 1. Well, that's exactly what we divide by there, f of 5. Let's go through a specific example. We have f of x comma y equals y e to the negative xy minus y for x and y both greater than 0. Now the marginal density associated with y, let's just perform the integral. We integrate from 0 to infinity of the joint density function over x because we want the marginal associated with y. And you can perform the integral. It works out to be e to the minus y. And then our conditional density then, f of x given y, is the joint density f of x comma y divided by f of y. So just churn through the calculations and you get y e to the negative x times y. And so if you wanted to know what's the conditional density, the governing behavior of the random variable x, given that y is, say, 3, then that density would be 3e to the negative x times 3. Okay, so you just plug in y equal 3. So now this function, if you plug in any possible value of y, this function will now give you the associated density function for the random variable x, conditioning on the information that y takes on that specific value. Okay, welcome back, troops. This is Mathematical Biostatistics Bootcamp Lecture 5, and we're going to start talking about Bayes' rule. Bayes' rule is one of the most famous results in statistics. It comes from I believe, Presbyterian minister named Thomas Bayes, who wrote down the rule I believe it was published posthumously much later, and it's an astoundingly simple rule that has incredible power to it. And the idea is basically, how can you relate conditional probabilities of the form A given B to probabilities of the form B given A? So you reverse the arguments. It's very important, right? It's saying, how can I talk about A given that B has occurred when I only know things about the distribution of B given that A has occurred? It's a very important thing. And of course, you can't do that without a little bit of extra information. And we'll talk about it specifically where that extra information comes from. I wanted to give the mathematical, the probability, density, and mass function version of it first. And then we'll talk about the kind of classical treatment with events. But let's let f of x given y be a conditional density or mass function for x given that y has occurred and has taken the value y, and f of y being the marginal density for y. Then if y is continuous, then Bayes' rule basically says that f of y given x is f of x given y times f of y divided by f of x given t times f of t dt. And notice that what we needed to know to do this calculation of f of y given x is f of x given y, and then this extra argument, f of y by itself. And so the idea of Bayes' rules is sort of flipping the arguments. And then if y is discrete, f of y given x is f of x given y times f of y divided by the sum over t of f of x given t times f of t. Bayes' rule, again, relates f of y given x to f of x given y, and then the marginal density f of y. And if we apply this to events, it takes a kind of familiar form that you may have run into before. So a special case of this relationship basically works out to be probability of B given A is the probability of A given B times the probability of B, divided by probability of A given B times the probability of B plus the probability of A given B complement times the probability of B complement. And you could do this exactly from our previous formula. Let x be a discrete random variable, that's the indicator of whether A has occurred, y be an indicator that the event B has occurred, then plug into the discrete version of Bayes' rule. That would be a simple proof if you were willing to stipulate the previous page. You can also prove it very easily just by working with the rules of probability and sets. So this numerator is probability of A intersect B. This denominator is probability of A intersect B plus probability of A intersect B complement. So the numerator works out to be probability of A intersect B. The denominator works out to be the probability of A. So that's exactly the conditional probability B given A. So it's quite easy to prove, but I just wanted to, by discussing this, indicate to you that there's no real distinction between the way we're discussing it in terms of continuous densities or discrete joint mass functions and this kind of traditional method of treatment using probabilities and events. So that's a very brief treatment of how you can use Bayes' rule with densities and with mass functions. We'll go through several examples next time, but one of the most common and biggest examples that we're going to talk about is associated with diagnostic testing, and that's what we'll do next. Okay, welcome back, troops. This is Lecture 5, Mathematical Biostatistics Bootcamp, and now we're going to be talking about diagnostic test. So a particular application of Bayes' rule, its use in so-called diagnostic testing. And we'll talk a little bit about the kind of traditional treatment of this, but we'll also delve a little bit into the intricacies of these calculations. They're a little bit more complex than people usually give them credit for. But the simple treatment is as follows. So let's let plus and minus be the events that a diagnostic test is either positive or negative, respectively. So plus being positive, of course, and minus being negative. And then let's let D and D complement be the event that a subject of the test does or does not have the disease, respectively. We can make a definition. The sensitivity of the test is the probability that the test is positive given that the subject actually has the disease. Probability of plus given D. That's the sensitivity. The specificity is the probability that the test is negative given that the subject does not have the disease. That is the probability of a minus given D complement. So let's give a couple more definitions. So the positive predictive value is often what a subject would want to know. That is the probability that a person has the disease given a positive test result. And the negative predictive value is another thing that people would very much so like to know in the result of a negative test, is the probability that they do not have the disease given that the test is actually negative. And then we might declare the prevalence of the disease to be just the marginal probability of disease. Okay, last set of definitions. The diagnostic likelihood ratio of a positive test, and let's call it DLR plus, is the probability of the test being positive given that the person has the disease divided by the probability the test is positive given that the person does not have the disease, which is exactly sensitivity divided by 1 minus specificity. The diagnostic likelihood ratio of a negative test, labeled DLR minus, you can read the formula there, probability of negative test given the disease divided by the probability of a negative test given disease complement, which is 1 minus the sensitivity divided by the specificity. Okay, we'll go through in detail why all these things are useful through a specific example. And then we'll come back and talk a little bit about maybe why these calculations are a little bit more subtle than people often discuss. Okay, so a study comparing the efficacy of HIV tests reports on an experiment which concluded that the antibody tests have a sensitivity of about 99.7 and a specificity of about 98.5. And I got these numbers from a website, but am fudging them a little bit because it's kind of more important to just perform the calculations than to talk about specific tests and to evaluate them. So imagine these numbers are accurate with respect to a specific test. And by the way, why Bayes' rule is kind of convenient in these sorts of settings, it's in principle a little bit easier to get these numbers, sensitivity and specificity, by virtue of the fact that you would just take blood samples for a set of people that you know are HIV positive and see the proportion of them that the test comes up positive, and you take a group of people that you know to be HIV negative and see the proportion that have a negative test result. And you could get these numbers or get estimates of these numbers. And of course, that's a very simplistic treatment of how you actually would get a sensitivity and specificity. There's lots of issues, like how do you actually know if you're working in an area where the tests are difficult, how do you actually know whether a person has the disease or not is in question. Or if you wait so long to where the disease is very clinically relevant, then are you evaluating the test in a stage of the disease where it's not interesting for when you would be applying the disease? There's a lot of issues in development of test and evaluation of test and constructing their validity that we are going to completely gloss over in this discussion. So for our discussion, let's just assume these numbers are right, that they work well. And then also let's assume that there's a 0.1% prevalence of HIV in the population, and a subject receives a positive test result. Well, what is the probability that this subject has HIV? Well, mathematically, what we want is the probability of disease given a positive test result, given the sensitivity, the probability of a positive test result given disease, which is 0.997. The specificity, probability of a negative test result given disease complement, 0.985, and the prevalence, probability of D, 0.001. So using Bayes' formula, we can just plug in. We get 0.997 times 0.001 divided by 0.997 times 0.001 plus 0.015 times 0.999. This works out to be about 6%. So it works out that a positive test result only suggests a 6% probability that the subject has the disease. Or in other words, the positive predictive value is 6% for this test. Now, you might wonder, that seems awfully low. Why is this the case? That, if I take a collection of blood samples that are known to be positive and I apply the test, it's 99% are accurately labeled as positive. How is this so low? And if I take a bunch of blood samples that I know to be negative and I apply the test, I get a very high percentage of negative tests. How is this so low? Well, it's basically the low positive predictive value is due to the low prevalence of disease and the somewhat modest specificity. It's not so bad. And In this case, this is what Bayes' rule actually does for us. You start out with prior information, basically, a very low probability of thinking that this person has the disease. Then you update it with the information of the positive test result, and that gets codified by updating it with the sensitivity and the specificity associated with the test, and that informs the positive predictive value, and you get something that's much higher than the prior probability of disease, the prevalence, but still isn't terribly high because you started with such a low prior. And that's how Bayes' rule works. So, for example, here the prevalence we're talking about is some, say, national prevalence in the U.S. But imagine if you knew that the subject was an intravenous drug user and routinely had intercourse with an HIV-infected partner. Well, your prior that this person has HIV would be much, much higher than the low prevalence that we cited here. I don't know what the prevalence is among a population like this, but suffice it to say that it's much higher. And then your positive predictive value would be similarly higher, which is kind of an interesting discussion. Imagine if you were a clinician of some sort and you were working with a patient and you saw their positive test result and you'd say, yeah, it's a positive test result, but maybe we should run another test or do some other things to evaluate your condition. The positive predictive value associated with this test is only 6%. Well, then in the same interview, it came out that the person was an intravenous drug user and routinely had intercourse with an HIV-infected partner. Well, then the clinician would say, oh, well, the test is very conclusive. We need to start you on antiretrovirals or something like that. So from the patient's perspective, that might seem a little odd that this external information is what kind of changed the conclusion. The test value didn't change. Just in the discussion with the clinician, only their prevalence changed, and only the prevalence in the calculation changed. So from the patient's perspective, this might seem a little weird. But again, the mathematics are exactly accurate. So there's a question as to what is the component of the calculation that does not change regardless of the prevalence? And that's ultimately what the diagnostic likelihood ratios are giving you. So take, for example, here, the probability of having disease given a positive test result. We use Bayes' rule, and you see Bayes' formula on the right, and the probability of not having disease given the positive test result. And then we see Bayes' rule on the right for that setting. If you take these two equations and divide them, you get the following very, very nifty formula. The probability of disease given a positive test result divided by the probability of not having disease given a positive test result is equal to the diagnostic likelihood ratio times the probability of disease divided by the probability of disease complement. So just to simplify this formula a little bit, we need to talk about odds. So odds has a formal mathematical definition. If you say the odds of something is 2 to 1, that's a ratio of 2, right? 2 divided by 1. That has an implied probability of 2/3 that the event occurs and then 1/3 that the event does not occur. So the way you go from probabilities to odds is you take the probability and divide it by 1 minus the probability. So in this case, take 2/3 and divide it by 1/3, you get 2, you get the odds. To go from odds back to a probability, you take the odds and then divide by 1 plus the odds. In this case, we had 2, take 2, divide it by 2 plus 1 or 3, you get the probability, 2/3, and then 1 minus the probability is 1/3. So if someone were to say the odds are 3 to 1, then that means the probability is 3/4 and the probability of the event not occurring is 1/4. If the odds are 4 to 1, that means the probability that the event occurs is 4/5, and the event that it doesn't occur is 1/5. Okay, so hopefully you get the picture. Work out some examples on pen and paper. Just to let you know, if you go to horse racing in the US, it's always the case that they give you the odds against something happening instead of the odds for it. So they're defining odds in terms of the odds against rather than the odds for. So anyway, that's just a small thing if you happen to go gambling this weekend. Okay, so in this formula, it has a very specific form then. The post-test odds of disease, probability of D given positive test result divided by the probability of D complement given a positive test result. So the post-test odds of D is equal to the diagnostic likelihood ratio times P of D divided by P of D complement, which is the pre-test odds of disease. So we have some inkling of whether or not a person has the disease just based on prior knowledge before we administer the test. We obtain the test, and that yields data. Well, the DLR plus, because it's a positive test, is the factor by which we multiply our pre-test odds to obtain our post-test odds. So in the discussion I was talking about earlier, whether the person is an intravenous drug user and has sex with an HIV positive partner is irrelevant to the DLR, right? The DLR says, for example, that your odds of disease has increased by X amount by virtue of having a positive test, regardless of your prevalence, right? Whereas the positive and negative predictive value inherently factor in the prevalence. Okay, so that's the reason why you get drastically different numbers for these things, because they're interpreted in different ways. So I also want to talk a little bit about this idea of Bayesian philosophy, and regardless of whether you're a Bayesian statistician, Bayesian philosophy is quite appealing. And this formula that the post-test odds is equal to the likelihood ratio, which is the probability model and the data combined times the pre-test odds, it's a very appealing sort of mirror to how we think the scientific process should work. You start out with an a priori kind of weighting of a set of hypotheses. In this case, it's sort of a hypothesis and its complement. And you collect data, and that data informs your belief. And then now you have a post-test odds of disease. And then suppose you were to actually run another test. Well, the likely starting point for your new prior would be the post-test odds, or the posterior after your first test. And it turns out it all works out just fine, that if you take two tests and they're both positive, your diagnostic likelihood ratios just multiply. But in terms of Bayesian think, it's the idea that you have a prior, you update it with data, you get a posterior. Now that posterior is your prior. It also codifies a lot of scientific discussion. If your prior is absolutely fixed at a specific point, then the data is irrelevant. Nothing's going to move you off of it. A lot of politics is that way, of course. So I think if you think about political discussions in terms of Bayes' rule, it's really not very surprising at all. So at any rate, let's just go through our HIV example in more detail. So suppose someone has a positive HIV test. The DLR plus is 0.997 divided by 1 minus 0.985, which works out to be about 66. So that means that regardless of your prior behavior in the population you're coming from, the virtue of this test is that now you have 66 times the pretest odds of having the disease. Or you could say, or equivalently, the hypothesis of disease is 66 times more likely, supported by the data, than the hypothesis of no disease. And then let's just go through another example. Suppose that the subject has a negative test result. Then the DLR minus is 1 minus 0.997 divided by 0.985, which works out to be about 0.003. So the DLR minus is telling you about your odds of disease and the result of a negative test result. So your factor that you're multiplying by is 0.003. So now your post-test odds is 0.3% of your pre-test odds given the negative test. I wanted to conclude with a discussion on kind of a very deep point associated with these calculations. These calculations are done, and there tends to be very little discussion of how much sense they actually make. So if you are, in fact, a Bayesian, then none of this has any problem whatsoever. Assigning a probability to the event that an individual has a disease offers no complications in Bayesian thinking. A probability to a Bayesian is not as much of an objective thing. It's a quantification of belief. So you have your prior belief, you have the component that is independent of your prior in the diagnostic likelihood ratio, and then you have your posterior belief, and that if you're consistent with respect to Bayes' rule, then your posterior belief has been multiplied appropriately by the diagnostic likelihood ratio vis-a-vis the data. And then you wind up with a very consistent picture. If you're a frequentist, then it's a little bit harder to think about these things because the standard frequentist sort of boilerplate line is that the person either has the disease or they don't. There's no probability associated with it. And if you're not being a Bayesian and that probability is not a mathematical codification of a belief, then it takes on a different character. You can still interpret the calculations, though, I would contend. Maybe some hardcore Bayesians would still find issue with how I'm proposing to interpret it as a frequentist. But still, I would say you're not talking about the probability that this specific subject has the disease in the frequentist sense because they either have the disease or they don't. There's no probability left. But what you're talking about is this idea of potential fictitious repetitions of this experiment and using the probability as a contextual entity to evaluate this person's probability of disease as context. It's probability if lots of people exactly like this person took this test, what would be the long run percentage of positive test results that we got. That sort of thinking is what I'm proposing is the way you could shoehorn these calculations into frequentist thought. And I think it's probably fine. Either way, churn through the mathematics in the same exact manner, but the interpretation is quite dicey. And I think it's probably fair to say that most statistics texts kind of gloss over some of these finer details because, admittedly, they're quite difficult to think about. The other thing I wanted to briefly touch on is the nature of actually collecting data to inform these calculations. And I touched on this a little bit before, but it's very difficult to know conclusively whether or not someone has a disease when you're developing a test, usually. And it's very difficult to develop things like actual real prevalence estimates that are relevant to the person that you're talking about with respect to the disease. It's also very difficult to have whatever samples you're using to develop sensitivity and specificity be indicative of the population of samples that the test will be applied to in actual clinical practice. So in the process of saying this, even though these calculations are very simple and they actually highlight Bayes' rule quite nicely. Actually, that's the primary point of the lecture is that they highlight Bayes' rule, and we've churned through some Bayes' rules calculations. But I don't want to give you the sense that this is all there is to the world of diagnostic testing and validation, which is a very, very deep subject and quite a fun subject, I might add, but involves quite a bit more than Bayes' rule. So thanks for attending the lecture. We'll see you next time.